September 30th, 2025. A quiet morning on Earth, but 400 million miles away, the largest planet in our solar system was hiding a secret that would overturn decades of scientific certainty. For centuries, Jupiter looked like a world we thought we understood. A gas giant with storms bigger than Earth and an interior we painted with neat, simple diagrams. But when NASA's Juno spacecraft finally slipped into its orbit and measured Jupiter with the highest precision ever achieved, the planet answered our questions with something no one expected. Beneath the swirling clouds, beneath the bands and storms, Jupiter was not what our textbooks had promised. It was hiding a massive structure, a structure so strange that it rewrote everything we thought we knew about giant planets. For most of the space age, Jupiter's interior was guesswork disguised as confidence. We could map its storms, track its lightning, even study its moons with incredible clarity. But once you looked past the clouds, everything became theoretical. Astrophysicists built models and argued over them, but the truth remained buried thousands of kilometers below the clouds. Some argued that Jupiter had no core at all, that it was just a gravitationally collapsed ball of hydrogen and helium, almost like a star that never ignited. In that picture, its center was nothing more than increasingly dense layers of gas pressing down on themselves. Others argued for the opposite extreme, that Jupiter formed just like the rocky planets, a solid core first, then gas wrapped around it. That core, they said, should be 10 Earth masses or more, a dense, compact nucleus buried beneath oceans of metallic hydrogen. Both ideas made sense, and both ideas had problems. The collapse model predicted a planet made almost entirely of hydrogen and helium. But the more we observed Jupiter, from Earth telescopes, from spacecraft, from Galileo's atmospheric probe, the more heavy elements we found. Carbon, nitrogen, oxygen, noble gases in quantities that simply didn't match a pure gravitational collapse. On the other hand, the core accretion model neatly explained those heavy elements. But then the questions began piling up. How large was that core supposed to be? Was it stable under unimaginable pressures? Why didn't Jupiter's gravitational field behave in ways that matched a simple, compact central mass? By the late 1990s, missions like Pioneer, Voyager, and Galileo had offered pieces of the puzzle, but none had penetrated deep enough to see the truth. Jupiter remained a mystery wrapped in cloud bands, and the two competing models lived side by side, each convincing, each incomplete. Astronomers knew that solving Jupiter's interior would answer more than a planetary mystery. It would answer how giant planets form everywhere, even around distant stars. That is why NASA built Juno, not to take pictures, not to admire the storms, but to measure Jupiter's gravity with the precision needed to weigh its interior layer by layer. The plan was simple. Every time Juno passed close to Jupiter, the planet's gravity would tug on the spacecraft. By watching how those tugs sped Juno up or slowed it down, scientists could reconstruct the way mass was distributed inside the planet. For the first time in human history, we would be able to see beneath Jupiter's clouds without going there. When Juno arrived in 2016, expectations were straightforward. It would confirm one theory or the other. Either Jupiter had no solid core, or it had a sharply defined one. But the universe rarely cooperates so neatly. When the first gravitational results came back in 2017, they didn't match either idea. In fact, they pointed to something far stranger than anything predicted. Jupiter didn't have a clean boundary. It didn't have a crisp, compact nucleus. Instead, the data revealed a massive, diffuse region, a vast, extended structure where heavy elements were spread out across an enormous portion of the planet's interior. It wasn't a core, not the way we imagine one. It was something else entirely. Jupiter, the largest planet in our solar system, had a fuzzy core. This was not supposed to be possible. Planets are built in layers, dense material sinks, light material floats, sharp boundaries are expected. But Juno showed Jupiter breaking those rules. Heavy elements weren't locked into a compact center. They were smeared outward, blending gradually into hydrogen and helium. The transition wasn't sharp. It was blurred, like a watercolor painting left in the rain. The question scientists asked next was simple. How do you get a structure like that? The first explanation reached back into the violent early solar system. Hundreds of millions of years after the Sun formed, gigantic collisions were common. Earth was struck by a Mars-sized body. Uranus was hit so hard it tilted sideways. Maybe Jupiter, too, suffered a catastrophic impact. If a protoplanet 10 or 20 Earth masses slammed into young Jupiter, it could have shattered a once solid core, scattering heavy elements outward and mixing them with the surrounding hydrogen. For a moment, this idea fit perfectly. It explained the fuzziness, the blurred density, the strange gravitational signature. The scenario was dramatic, elegant, and exciting. But science doesn't stop at ideas. It tests them. When researchers ran supercomputer simulations, they discovered a major problem. The impact would indeed blur and disperse heavy elements, but not permanently. Over time, gravity would pull those materials back inward. The core would reform, compact and sharp once again. After millions of years, the fuzziness would disappear, but Jupiter's fuzziness is still there billions of years later. The impact idea began to fall apart. So scientists turned to Jupiter's formation itself. Maybe the fuzziness didn't come from destruction. Maybe it came from birth. In this model, heavy elements didn't stay locked in a solid seed. As Jupiter grew, those materials dissolved into the surrounding hydrogen and helium, creating gradual layers where composition changed slowly rather than abruptly. Instead of a clean core and envelope, the planet formed with a smooth gradient. But this only works if Jupiter's interior doesn't mix. If it were fully convective like Earth's mantle, those gradients would have been erased long ago. But Juno's measurements suggested large regions inside Jupiter are stable and non-convective. That stability allows gradients to survive for billions of years, preserving a diffuse interior instead of collapsing into a compact core. When this idea was combined with Juno's observations, the picture finally made sense. Jupiter may have started with a solid core, but over time, heavy elements bled outward, mixing slowly with hydrogen and helium. Without full convection to stir it back together, the blurring stayed. The result is the massive structure that Juno detected, a fuzzy core unlike anything we once imagined. Then came the next surprise. When researchers looked at Saturn, they found the same pattern. Cassini never dove into Saturn the way Juno did with Jupiter, but it did something remarkable. It studied waves in Saturn's rings. Those waves act like seismographs carrying the imprint of vibrations traveling through Saturn's interior. When scientists analyzed them, paired with gravitational data, they found the same signature. Saturn, too, has a fuzzy core. Heavy elements spread across a large region. No sharp boundary, no compact nucleus. If both Jupiter and Saturn have fuzzy cores, then fuzziness is not a rare exception. It might be the rule for giant planets. This pushed scientists to rethink giant planets around other stars. For decades, exoplanets were modeled with neat layers and hard boundaries, but thousands of discoveries began to challenge that, especially hot Jupiters, massive planets orbiting extremely close to their stars. Many of them are far puffier and hotter than simple models can explain. But if these worlds also have fuzzy interiors, with heavy elements blended gradually outward, everything makes more sense. Those gradients slow cooling, alter heat flow, and influence atmospheric chemistry. Suddenly, the inflated sizes of hot Jupiters no longer look mysterious. They look like part of a pattern, the same pattern Juno uncovered. But the fuzzy core wasn't the only revelation. Jupiter's magnetic field turned out to be even stranger. We knew it was strong, the strongest of any planet, stretching so far into space that it reaches beyond Saturn's orbit. But Juno showed the field is incredibly lopsided. Multiple south poles, strange patches of intense magnetism, irregularities that don't match simple dynamo theory. On Earth, liquid iron in the outer core creates our magnetic field with organized flows. Jupiter should work the same way, except using metallic hydrogen. A fast-spinning planet should produce a fairly symmetric field, but Jupiter doesn't. The fuzziness complicates the picture instead of clarifying it. The diffuse core changes how material moves, how heat transports, how the dynamo operates. Some regions may conduct differently, some may rotate differently, some may create small dynamos inside the larger one. Add possible helium rain, droplets sinking through the interior, and the complexity becomes staggering. Jupiter's magnetic field refuses to behave simply because Jupiter refuses to be simple. And the result is stunning. Constant auroras that never turn off, hundreds of times more energetic than Earth's, powered not only by the sun, but by the dynamics deep within Jupiter itself. Even now, after Juno's final dive into Jupiter in late September 2025, new studies continue reshaping our understanding. This year, teams using massive collision models found that giant impacts don't leave fuzzy cores behind for billions of years. They eventually collapse back into compact ones. That means Jupiter's fuzziness must be the result of formation and long-term evolution, not a single explosion in its past. Other researchers explored how internal waves move through Jupiter, showing that the fuzzy core changes how sound waves, gravity waves, and inertial waves travel. This opens the door to a new kind of planetary seismology, a way to map Jupiter's interior the way we map Earth's using earthquakes. The more we learn, the clearer the truth becomes. Jupiter isn't a planet with a simple core or no core. It is a world with a massive, diffuse, evolving internal structure that challenges our assumptions about planet formation. Saturn likely shares that structure. Exoplanets may follow the same pattern. Fuzziness may be a fundamental part of what makes a giant planet a giant planet. And with each discovery, Jupiter forces us to rewrite our models, rethink our theories, and accept that even the largest worlds can remain mysterious. What Juno revealed is not just a fuzzy core, but a new understanding of how planets form, evolve, and behave. Jupiter is not the world we once imagined. It is stranger, more complex, more dynamic, and more layered than any textbook ever described. And the massive structure hidden inside it, the structure Juno uncovered, stands as a reminder that the universe still has surprises waiting deep beneath the clouds.